to do this trick.
Yeah.
C'est bon? You think it's okay?
Yeah, I think it's fine.
Does it work, this?
You can check.
Can I change what is the title of my presentation? Because I didn't put that. So
It's fine, it's fine.
This one.
This one, right?
Yeah. Can you have the agenda?
Yeah, I do have the agenda.
Yeah. Can you?
This is the agenda.
Can you copy paste this and change the title of my presentation?
So is this one, right? It's not the same. Quality, what is this calibrate?
That's good. You can just move this.
Okay. Just okay?
Yeah.
Do you want me to copy my right now, or?
No, I can, because we have at least 2 minutes
Yes.
between each presenter.
Yes.
Is enough
Okay.
time to
Yeah,
copy.
yeah. And then basically I am speaking from this.
Yeah,
Right?
it's to turn on. It's here, but you need also to turn off.
Yeah. Okay.
It takes 1 minute to.
How I understand that it's turned on.
There is some light.
Okay.
Some light.
Yeah. Okay. Here. Yes. But then they were speaking through this microphone.
Huh?
They are going to speak.
No, or you can, but just to have the sound. Okay.
But this sound would go out. Will be spread in a room.
Yes.
C'est super.
It's not on, so you just press it. Yeah, now it's on.
Where are you going to sit?
I will be there on that corner.
Because I will need the stick at some point.
The stick, Igor has the stick now because he's copying.
Okay.
So, but we have 2 minutes to copy, so I think it's not a big deal. Right?
Yeah, but I have to get the stick.
Yeah, I know. A bit.
Okay, so I'll get it from Igor.
Here,
Yes.
Igor. Do you have any?
What?
Do you need any presentation, agenda or something?
Oh, I do. I have it here. You want to show it, or?
I can show. That's
Yeah, you
no
can show
point.
it. Yes.
All right. So
Yeah, I think we can start.
I will support.
Yeah. Okay, good morning, everyone. So this is the time to start our short workshop. We organized quite quickly. It was an idea which originally came from Sebastian from Nokia Technologies. We knew that Patrick and Federica were going to be around, and we thought that it is good to put together a few interesting talks under the name of Immersive Quality of Experience. You have seen the agenda, so we are going to have 4 talks. There is coffee outside, so if you need coffee or some other refreshment, please feel free to fill in your cups and to come back to the room. Our first talk is by Professor Patrick Callet, who I'm going to read your bio, yes. Oh, yes. It's a bit long, but yeah. Received both MSc and PhD degree in image processing from École Polytechnique de l'Université de Nantes. He was also student at École Normale Supérieure de Cachan, where he studied the aggregation in electronics of the French National Education, worked as a assistant professor, and then he is currently a full professor in engineering school in the University of Nantes. He led for 10 years the Image and Video Communication Lab at CNRS, and was one of the 5 members of the steering boards of CNRS IRCCUN. So this is the old acronym of the lab. Scientific director of the cluster West Industries Creatives. 5-year program gathering more than 10 institutions, including 3 universities. He is mostly engaged in research dealing with the application of human visual modeling in image and video processing. His current centers of interest are quality of experience assessment, visual attention modeling and application, perceptual video coding, and immersive media processing. He is co-author of more than 250 publications and communications, and co-inventor of 16 international patents on these topics. Serves and has been served as associate editor or guest editor for numerous journals. Okay, so the topic is objective quality metrics for quality of experience and immersive media. And I think it's time to give you the floor, please.
Thank you very much, Atanas. Nice introduction. Better than 3D TV conference one, I would say.
I'm improving.
Yeah, you are improving, so it's good. Is the sound okay? It's okay, the sound? Yeah. I don't know how to access my presentation, actually. That's, maybe it's here. Okay. Okay, perfect. This thing is working. Okay. Good morning, everyone. For some of you, some of this presentation will be a little bit of a recap of what you have seen at 2D TV conference, but I try to make some new things and new ideas here. So the duty was not that clear to me what I should present here, considering the venue, considering the audience. So I decided to give you some thoughts about what's my vision, the problems that I can foresee in terms of evaluating quality of experience, and mostly for this talk, image and video quality for immersive media. When we are talking these days of multi-views, 3 degrees of freedom, 6 degrees of freedom, and so on, what does it mean exactly? Considering what has been done in image quality assessment communities so far. So it's mainly ideas, challenges. There is no, I would say, a lot of solution in what I'm going to present, but at least some warning and things that we should avoid to do, and few observations that we get from different experiments. So just to so it doesn't work? Oh my God. I need your help. Yes, maybe because the one which is, yes, maybe I should use this, right? Yeah, this should be the, okay. Yes, so as a first warning, I want to report to you a story about, this is an old story actually, more than 10 years ago, when we started to investigate how image quality metrics, that means algorithm that has been developed to predict computationally the image quality, how, depending on what they are considering or not, how they are robust to different viewing conditions. And on this chart, you can see how, for instance, SSIM, very well known, let's say the new PSNR metric to evaluate image quality. So SSIM stands for Structural Similarity Metric, something that has been quite widely adopted, especially in some venues like MPEG these days. This is on this chart. You have how SSIM is performing in predicting mean opinion score, which mean which are the score provided by observers when they are watching different images and they have to rate the quality of images. And here we are looking at the correlation coefficient between SSIM and the subjective scores coming from this type of experiment. And you have here 3 data sets which are under study. So what is changing between this data set? You have the protocol, the way you record the rating. So here you have, for instance, the double stimulus impairment scale. Here this is a single stimulus continuous quality scale. Here it's absolute category rating. So we play with the rating scale here. And we play also with the display condition. At that time, LCD were appearing, and we were comparing the quality using, for instance, CRT display compared to LCD. And as you can see, SSIM, in terms of correlation with subjective score, is not really robust. It's not robust, and the main reason for that is that this metric operates in pixel domain, but does not consider at all viewing conditions, namely the viewing distance, the characteristics of the display. So it doesn't consider what actually reach the signals that is reaching the eyes. And so so probably it has been tuned in conditions which are closer to this one, but when you start to change the viewing distance, you start to change the display and so on, then you lose robustness. And at that time, we were proposing another metric that was considering, for instance, the display properties. So in the front end of the matrix, you have something which is adapting that goes from pixel to let's say luminance domain, and then you can achieve better robustness. But just a big warning here is that don't take a tool, PSNR, SSIM, or whatever it is, to try to, don't expect that it's going to predict your image quality perfectly if you are not introducing a little bit of context. So there have been a lot of metrics that has been developed along years. There are, I would say, a few hundred available to predict the image or video quality. But I should say that most of them are working in a kind of little space of among the hyperspace of possibilities that you can encounter in real life scenario. What I mean by that is that most of the metrics, all the metrics, to validate them, to understand if they are performing well or not, they are validated on ground truth, which is the result of subjective assessment protocols or subjective assessment experiments. And the way you design this subjective experiment is kind of somehow can bias the result that you obtain. So in real life, you have to deal with different type of content. You have to deal with different type of distortion level, different type of distortions, lokiness, blurriness. As we are introducing new codec, for instance, we have new type of distortion which are appearing. We have, in terms of content type, you can describe your content in terms of spatial information, temporal information, depth information, color information, and so on. So when you want to design a subjective experiment and to understand how the quality is affected by these different factors, you have to explore all these things. But as a matter of fact, if you look at what we have when we study this type of problem and we run subjective experiment, because they are timely, consuming, and so on, we mostly explore a little part of this space. And all the metrics that we're going to tune, validate, and so on, likely works in this little part of the space. So generalization and so on is not, that's not very interesting. And these days, in the era of deep learning, people, of course, use a lot of deep learning techniques and so on, which are very good to learn what's going on here, but probably not, because this is the ground truth that they have, but probably not able to expand and to be robust out of this little space. So do we learn much when we do this type of things? I'm not sure. This is why people have tried to develop also methodology to the art of designing good subjective experiment. I like this sentence, and I like to quote usually this sentence from Phil Corriveau. So Phil Corriveau, for those who don't know him, was one of the founder of VQEG, Video Quality Expert Group, in the mid-90s. And he's used to say that a metric, a quality metric, is only valid under the condition on which it has been tested. And I think that's a very wise sentence to take off. And as I said before, don't take a tool and expect that it's going to work outside of this. So of course, when we are talking about immersive media, 3DOF, 6DOF, we are playing with also new type of viewing experience, which can be considered as another dimension to tackle. And once again, if you have a metric that works well for previous conditions, there is no objective reason why it should work for this new viewing experience. So we have some of them here. High dynamic range was kind of challenging, and we have some evidence that traditional metric doesn't work for these type of things. Stereoscopic 3D TV has to be requires also the design of new metrics, and as free viewpoint TV and so on. Okay, so I'm not going to touch this problem here, the content type, because I think Federica will present in the next talk some things that we have investigated together on how to address this content type for immersive media. But yes, I want to stress now that for multi-view videos or VR or 3 degree of freedom or 6 degree of freedom case, we are definitely missing proper metric to do that. And I want to illustrate that with few data sets that we have produced and give you some evidence of that. One of the reasons why we don't have a proper metric for that is because most of the metrics that has been designed before have been tuned on specific artifacts. And with this new scenario, we have very, very special artifacts that has not been considered before, especially object shifting, geometric distortion, SSIM, PSNR, all these type of metric, they are not able to do to tackle this problem, geometric distortion. You have also these impeding techniques, flickering, and so on. And one thing which is also appearing with multi-view content or let's say immersive media is that most of the artifacts that we're going to observe are very localized. So they are not, let's say, we cannot consider that the image is uniformly affected by a codec or whatever recipe is used to transmit this. While PSNR, SSIM, all these type of metrics are usually considering that the distortion is uniform. And this is not the case for immersive media. So there is poor hope that this thing will work properly. So that's just an introduction of what I want to discuss now. Let's say we will be in that scenario to present some of the results. So let's say we have a transmitted view. Eventually, we can render and synthesize new views on the rendering side. So there are many sources of artifact here that comes first on how you compress and you transmit these views, and then there are other artifacts that comes from the synthesized algorithms that are used, or DIBR algorithm that are used to generate this synthesized view on the viewing side, the rendering side. So one thing that was kind of interesting for us is that if you are in the context of free viewpoint TV or interactive scenario, basically you let the observers to switch from one view to another as he wants. Okay? And what are the effects of this? That's some stuff that we wanted to study. So let me introduce you some results from a first data set. So the idea here was to check what is the effect of DIBR algorithm. When we have two reference views, we can play with baseline, okay, between these two reference views, and we try to generate intermediate views. And in that case, so the artifacts comes only from the synthesized algo. So it's still image, time freezing, looking at the effect of Yes, this DIBR algorithm. So those DIBR algorithm can introduce very strange artifacts like shifting artifact, crumbling artifacts. So you have a lot of things that are not that usual in other so far considered scenario for image and video quality assessment development. So the problem is that the usual image quality metrics are mainly based on values of signal characteristics, but pixel-based, and they cannot fully capture this type of artifact. And if you look how they perform in terms of correlation with human mean opinion score, so the experiment that we ran before, you can see that they are miserably failed. The correlation is not more than 0.3. So that's when I said don't use a metric out of this context, that's a lesson learned. So especially for this DIBR-like or generated artifact, this doesn't work at all. Still, okay. People have tried to propose metrics to address this scenario, especially the DIBR one. So people have fortunately offer some solution for that. So they went from beyond usual quality metrics, and the common ground of all these metrics is that they quantify the change on contours, and they consider that because the distortion on contours is kind of proxy for semantic level annoyance, and they were kind of successful because, yes, so the first one that has been introduced was VSQA, and on the database that was mentioning before, you can see that now we are much better, right? The correlation with mean opinion score improved from 0.3. Now we have some tools available here that can reach almost 0.9 correlation coefficient. Unfortunately, I don't think that this metric has been adopted by MPEG yet. So that's something we did together with Federica and Marco, this one. And then when we did that, I don't remember. 2013? Yeah, 2013, and now that's the latest state of the art. So yes, we gain progressively things for that scenario. You may wonder how it works when we go for video. So that's another data set that we produce. So this time, instead of, that's more or less the same idea. You have reference views, you can play with baseline, and you look at the quality of a virtual view, but this time, instead of freezing the time, now we look what's going on all a long time. So this is really a video that we are generating here. And we consider also now some compression artifacts. So we have also compression here. It's not only view synthesis artifact, but also coding artifact. These are the performance of commonly used metrics, once again, on this data set. So it's a little bit better than the previous scenario, because it's not only synthesized artifact here, you have also compression. But as you can see, the best one, which is VSNR, only reach a correlation coefficient around 0.5. So we are not yet there. So even for that scenario, it's not working well. Another data set, or another way to see this problem, because going towards, let's say, interactivity, is to understand what's going on when you start to, let's say, move between views. So in this data set, what we did, we use once again a view synthesis algorithm. We have some reference view, transmitted view. So we have encoding map, texture, depth map are encoded, and we can generate with, let's say, in that case, I think it was VSRS, from the tool that is used within MPEG for view synthesis. We look at what's going on when you freeze the time, you go from that view, and what's going on if from that view, you generate a kind of pseudo video moving from one frame after the other, from one view to the other. So, and in that data set, it was a kind of back and forward video. Okay, so what's going on? It's like a matrix movie-like video. And once again, if you look at the result of traditional metric, PSNR, SSIM, and so on, this is the correlation that you get. So you have both Pearson and Spearman correlation here. This is a correlation that you get with these metrics for that type of scenario. I should have shown you some examples, but when you do this type of view, you navigate between the views, you are introducing amazing artifacts, especially if depth map is not well encoding. But traditional metrics are not able to compute that. And finally, recently we investigate the following problem. So now it's really a free navigation scenario, kind of. And so we have reference view, transmitted, compressed, and so on. And we synthesize view again. But then we design some kind of trajectory along time. When we move from one view to another, sometimes we spend more time on some views that contains important object. So we did several experiments to understand how the trajectory can affect actually, it can eventually be an influencing factor on the user experience. So, because that's a problem. If you want to test any system here, which trajectory should you use? You can let any observers experiment what he wants to do with the content, but then it's very difficult to draw some big conclusion, because from one observer to another one, you will get different opinion score. So how do you average that? And inter-observer variability is pretty high. So another alternative is to say, okay, let's try to define several trajectories, the same for all the observers, and generate this pseudo video and compare the mean opinion scores that we get from one trajectory to another, and try to understand if it's an influencing factor. If it is an influencing factor, that's important, because then it may raise the fact that you need, then when you want to compare codec, you need a methodology to select the critical trajectories. So just for sake of time, I'm going to introduce a little bit how it works here, but that's not that important. So we consider that we have different views, reference views, encoded camera, synthesized camera based on encoded camera, and so on, and we define trajectory a long time there. So we can generate trajectory as we want. Just here, just to illustrate, we have, in that case, two types of trajectory, and one which is more focusing on object of interest. So we stay a little bit longer on these views. And these are example of results that we get for one sequence. So for these two trajectories that I presented before, you have here the mean opinion score obtained for these different trajectory, and we play here with baseline, coding parameters, and so on. And we observe actually that, the trajectory was kind of affecting, and it depends on the quality. So for high quality, the mean opinion score that you get with trajectory 2 is higher than the one that you get for trajectory 1. And when you reach lower quality, it's the other way around. So it's not only a matter of trajectory seems to be an influencing factor, but also the bit rate that you are using is an influencing factor also between trajectories. So sometimes trajectories are more critical for some bit rates than some others. So we run ANOVA and so on to better understand that if this was really an influencing factor, and it seems that yes, trajectory is an influencing factor. So testing this type of things, we are in trouble now in MPEG. Or to test codec and so on, we are in trouble because you need now a good methodology to select your trajectory and critical trajectory to take decision with codec. The thing that may happen is that for one given trajectory, one interactive scenario, let's say, one way to interact with the content, codec A can be better than codec B. But for another one, it will be the other way around. So that's opened a lot of questions and how we should deal with this problem. Okay. Of course, can we do better than the traditional metric to capture the quality? Because hopefully, if we have an objective tool that is performing well for this type of scenario, then we can fix part of the problem. So the last 2 years we tried to address this problem, and actually we investigate several representation domain with a common ground, which is we track the geometric distortion. As I stated before, the problem that we get with this use case scenario is that we are introducing a lot of geometric distortion and very localized geometric distortion. So can we find a good representation domain to track this distortion? So we propose different things for that. Some are based on a sketch token approach. So we have a kind of dictionary of sketch token things, and when we, for instance, check two views, we have some kind of self-extraction. We extract features and make some kind of registration between the two views, and then we compare this based on a dictionary. So each patch is described as a set of sketch tokens which are representing somehow the structural information. So this type of representation can be useful to track the geometric distortion. Another approach that we have tried is to do some elastic metric. So when you have, let's say, these two lines, we have a metric that is based on elastic matching, and try to measure how the curve has been modified, and this is given kind of good result. That's another representation that we have tested is related to convolutional sparse coding. So once again, from data set, we build some kind of dictionary that is based on this CSC representation, and we learn a lot of things. We have a learning process when we basically learn how the structural information is organized, and we learn the geometry of a patch, and then we can get some pretty good result also with this type of representation. But it's still ongoing, and extension to a temporal case is currently one of the focus of our work. Okay, so that was my stuff for multi-view. If I still have time, and I think I have a little bit of time, I want to touch another problem. So for the guys who were at 3D TV conference, you know a little bit about this story. But I want to speak a little bit about 360 relationship, how we can evaluate quality for another type of immersive media, and especially in 360, and the role of visual attention and saliency in that field. So saliency model or visual attention model. So for those of you who are not familiar with that, is something that tells you what are the most likely the area of the image that's going to be most likely seen or observed by people. So you can record that with eye trackers, but you have also computational model of that. That means that models that take that input an image or a video and tells you, okay, these are the regions that are of interest or likely of interest for observers. So this is a useful knowledge in many multimedia applications. You can do non-uniform video coding with that, and trying to preserve the region of interest, assigning more quality there, or more bitrate. It's pretty useful also for 3D TV or stereoscopic application, especially to better handle comfort, trying to limit accommodation, divergence, conflict in the region of interest. And it's useful also for high dynamic range and other fields. It's also a nice proxy for quality of experience, and especially to better understand the artistic intent. So I didn't have the time to explain that at 3D TV Conf. I'm going to explain this a little bit more, so open your ears eventually. So I don't know if you know this picture. Someone knows this picture? Yes, you know. But it's from a photographer, a French one. I'm French. Cartier-Bresson, if you know Bresson. So he was a guy till the end of his life, he was always roaming in Paris with his Leica camera and trying to capture a lot of things of life, especially Paris life. So this picture from Bresson is named un instant décisif, a decisive moment. And I guess you get the picture, right? He could capture this moment where the reflection of the guy on the water are just about to reach together, right? So if you look at this image, you have, of course, these things which are kind of interesting, but also there's this motion, movement, emphasized by horizontal stuff. And okay. So a few years back, we developed a computational model for visual attention, and Scott Daly, he was with Sharp at that time, now he's with Dolby, asked me, can you compute the output of your visual attention model for this image? I said, okay. So we did it, and he was giving a talk it was for the preparation of a talk at Electronic Imaging on artistic intent, and the role of artistic intent and image quality. And this is the output of the model. So this is a traditional heat map, and basically what it says, warmer is a color, so let's say yellowish, reddish here. The more likely it's going to be salient for observers. And as you can see, the output of this model gives you pretty good insight of likely what Cartier-Bresson wanted to capture, especially these things appears to be salient out of the model. And you have also some kind of horizontal things which are captured here. So this is pretty good because if you have such knowledge and you can model that, you have a computational model which is able to predict that, then you can probably do better encoding or have some kind of a strategy to preserve these areas. So somehow it's good because it's a way to capture artistic intent. So coming back to 360, visual attention and saliency modeling and so on for 360 can be very useful. Especially it has been widely investigated and in MPEG for viewport encoding and streaming, non-uniform quality streaming. There was a lot of discussion on what is the best way to represent a 360 content and encode it for interactive streaming, considering that the people don't see the 360, all the 360 at the same time, so you should put the quality on the viewport. It's useful for artistic intent storytelling, and eventually it can be useful also to compute the quality of a 360 encoded, decoded stream and so on. So one question that has been raised, if you want to compute the quality here, okay, let's say you want to use PSNR, where you should compute the PSNR? In the viewport, on the sphere, or in equirectangular representation? So this has been investigated by some people, especially Touraj Ebrahimi group, and they presented some result at PCS 2016. But yes, the problem is that if you go for equirectangular image here and you don't have any strategy regarding the sampling, it's very biased metric because you have, let's say if you consider the sphere, the points that represent the equator on equirectangular format are the same in here for the pole, while the pole is only one point on the sphere. So going for PSNR here won't be a good idea. So some people try to weight PSNR considering saliency. And that's something proposed by people from Stanford. They said, okay, let's take the PSNR formula and add just a weight, which is dependent on the saliency, but how to get the saliency map. So the easy way, and this is what they did, was to consider, okay, we have a head-mounted display. On head-mounted display, it comes for free. Most of them give you the position of the viewport, so the center of the viewport, just tracking the head, and that's a minimum feature if you want interactivity with HMD. So you can get that. And the idea was to build a saliency map where they consider that given the position of the viewport, all the pixels within the viewport are equally attended. So for one position of the viewport, they take the respective size, put 1 for all this, the pixel of this viewport, and as you have the all the head position or viewport position for, let's say, a certain viewing time, you can aggregate that, and finally you get this type of saliency map here in equirectangular format that tells you what are likely the position of the viewports, okay, or the pixels that can be seen. Okay, so they use that. So it's kind of saliency map from head movement, considering that we look everything in the viewport, which is a big hypothesis because it's very difficult to see all the pixels in 100 degrees at a given time. Okay, so we revisit this because we had a eye tracker embedded in HMD. So we wanted to investigate a little bit more of these things. So we compare actually a saliency map from head movement, considering the entire movement. And here, what could be a saliency map from head movement, but using just a Gaussian center in the middle of the viewport, which is what people are usually doing in computational modeling of visual attention. So you see that if you consider, for instance, a 2-degree Gaussian center on the middle of the viewport, which is 2 degrees corresponds more or less to the size of the fovea, you get this type of saliency map. But this consider that actually we look at the center of the viewport. And we were not sure about that. So this is why we run this experiment. So we use a HMD Oculus TK2 and plus an SMI eye tracker embedded in a HMD. And we could record the head rotation plus the eye gaze and the timestamps and everything. So we had head movement, head rotation, and eye gaze. So we did that with several observers, several type of content, and so on. And the thing that was kind of surprising is when we aggregate all the results across observers, content, and so on, we could derive this kind of PDF, probability density function, of where the gaze location are happening. So in x-axis here, you have the viewing angle difference between the viewport center and the gaze location. And you get this probability when you aggregate everything across observers, content, and time. And as you can see, the peak of this distribution is not the center of the viewport. It's a bit shift. It's quite shift. It's around, the peak is around 12, 14 degrees. Okay, so most of the gaze fixation are happening there. If you look at if you have content influence, you'll see that it's happening whatever the type of scenes. Indoor scenes, outdoor scenes, scenes with human face, you have always the relative gaze point difference from the viewport center and the gaze, it's almost always at the same location. Another funny thing is that this distribution, that's another way to look at that, now we consider the direction, is isotropic. So there is no bias, horizontal, vertical. So from the center, and you have a kind of all the directions are concerned by this bias. Okay. So we call this shape the donut, and so we don't look at the center of the viewport. So using a Gaussian from Edmond, let's say if you have the knowledge of the center of the viewport, using Gaussian to then try to figure out the possible saliency map is not the right way to go. You should better use a donut distribution. So that was kind of surprising result. We discussed that with a lot of people, and why is so? And we think that it might be an ecological process. So if you want to explore in 360, you have to consider that moving the eyes is less costly than moving the head. Okay, so we don't explore with our head. We can explore with the head when we want really to 360, but most of the information, the visual information that we grab is with our eyes. And especially if you want to look things which are on the top, it's better to move your eyes first than doing this or this. Okay, so that's why we say, okay, it's probably an ecological process. So more or less you stabilize your viewport, and then you grab information on very peripheral area if you consider that the center of viewport can be the center of your fovea. And another thing is that when you are looking in 360, you are not constantly moving your head neither, because it will easily trigger motion sickness. So people get tuned to that. They don't want to constantly move the head. So you explore with your eyes. You don't explore with your head. So definitely, we should not use the make the assumption that we look at the center of the viewport. And that's a recommendation for a systematic weighting. If you don't have eye tracker and you don't have yet a computational model for visual attention in 360, at least you can get the head motion data that comes for free. And if you just convolve this head motion data with the donut shape, then you get a fairly good approximation of what has been looked at in 360. And that's a fairly systematic content-wise weighting for head motion data, and you can use it for PSNR or whatever. So just to illustrate what it gives as a result, you have the ground truth here for this 360 panorama. This is what you do with from head motion, the stupid way, considering that you see everything in the viewport, and not just considering the data that comes from the head motion, convolving with the donut, you get that result. And that's pretty good, let's say, approximation of what you would get with an eye tracker, if you had an eye tracker in your HMD. Okay, that was the last thought I wanted to give to you. So thank you very much for your attention.
Thank you very much.
Yeah.
We have time for questions. Please, your questions.
The metrics that you introduced, are they available for us to use them too? Like,
You mean I think so, yeah. So this it's a bunch of it might be more hybrid than just one language, because but some are definitely yeah, available. The complexity is another question. Yeah.
Other questions, please.
This last study that you presented, that was done with images, if I understood right. Are you planning to repeat the same video? And what would be your expectation of it?
Okay, so actually it's not only planned, it has been done.
Okay.
Okay, so one of the purpose of this work, or motivation of this work, was actually to drive the people who are working on visual attention modeling, to drive them to address this type of scenario, because we have tons of models for 2D, or let's say visual attention model prediction for 2D scenario, but we don't have anything for 360. So last year we organized a grand challenge as part of a IEEE ICME conference, and that was targeting still image 360, and we ran all this experiment, provided a data set, and there were, I think, more than 30 models proposed from the community, including some model from Roma 3, and we get pretty decent results. So, and because it was kind of successful, you know, more than 30 models, so we were not expecting that much for. ICME asked us to organize a new challenge this year, and this year is about video. So we have kind of similar results. They are cooking now. We are presenting data sets and some of these results here. And about the models themselves, so the result of the grand challenge will be presented in July in San Diego. So stay tuned.
Right. More questions?
We have time to have a question at the coffee.
Yeah, but I have a question.
Ah, you have a question.
What about this game with all these metrics? Now, everyone is designing a metric showing that it somehow outperforms the previous ones, and they are all validated over some subjective tests. So what is the way to eventually adopt a metric and start using it and not to,
Okay.
I don't know. You got the question.
I got the question, yeah. But the answer, I'm not sure. So that was more or less what I wanted to illustrate here. Especially if we are looking at the old data set. It's a little bit like the visual attention modeling problem. A lot of efforts are dedicated to a small bubble of the, and people are just providing some kind of incremental result, and we're reaching saturation of result, and especially with deep net approach. So I think that there are three paths that people are trying to follow these days. First of all, the art of designing data set. Second, how to evaluate the metrics. And we don't learn that much from correlation, coefficient, RMSE, and so on. Even if I have presented that, these were figure of merit criteria defined by ITU, VQueg 20 years ago. And these days, we realize that they are not enough actually to seek for robustness. It's like a little bit software development. You don't care if your software works 95% of the time. It's the 5% where it's not working that you have to fix it. And that's a little bit the same for quality metrics. If you look the thing from correlation coefficient point of view, you're gonna lose that accuracy, this level of detail. So people now are developing framework to better identify where the metrics are not working. And you learn more from the bugs, and you fix your metric then. So that's the second thing. And the third thing is that how do you build the ground truth? It's not only about the test conditions. It's about how you get the score from your observers and how you process them. And once again, statistical framework are now on the grill to better robustify your estimate of your ground truth.
What is the proper body or organization to make this? Is it MPEG or ITU or VQueg, or is there any need of another one? Or
so, what is the landscape for quality assessment? First of all, what are the channels between these groups? And that's questionable. Now, what do we have on the landscape? We have Qualinet. It's a forum. We have VQueg. It's a forum also, expert forum, but with some connection with ITU. So VQueg is not a standardization body. Qualinet is not a standardization body. There are a group of experts who are thinking about stuff like that and then can inject some ideas there. So, and in terms of standardization effort, what do we have? ITU for this type of things, and IEEE. Especially you have one standard activity, a group named Human Factors for Visual Experience. And I would say that both group or both standard group have different policy, different way to proceed and so on. There are some, and different latency. Different latency. So, but that... okay.
Plenty to explore.
Plenty to explore. Efficiency of all these things these days and communication channel, I'm not sure. That's also, part of the game, because each time, let's say, for instance, ITU try to address something, it's for specific distortion level, and by the time you fix that, you have the good metrics there, then MPEG is coming with new type of artifact and new type of scenario. So, kind of chicken and egg problem. Other question?
Yeah.
Yes. Right. Could I just ask about the question of the relationship between the gaze position and the viewport? We know generally that where you look in an image is determined by the task that you've been asked to do.
That's true.
What task were people asked to do in the work that you were doing, and how robust is your donut model to different types of tasks?
That, okay. So just to be clear, in that experiment, where is that? It was a free viewing task. See, I didn't explain that properly, but the task was this one. View as naturally as possible. Okay. So when it comes to visual attention, yes, you're right. There are two streams, the bottom-up one, the top-down. Bottom-up is mostly driven by signals, properties themselves, and top-down is driven by the observers, what he wants to do. And even in that case, in free viewing task, observers assign himself a task, right? So I would say that what we get here is really for free viewing condition. I would not extend that to the way we look at the things for specific tasks. Now, then you need usually the way it is tackled in some visual attention computational model is that then you define the task, you understand what it is, and then you try to inject that in your model, and you have some kind of top-down branch to do that. Nevertheless, for this experiment, those who propose models at the ICME Grand Challenge that I mentioned later on, they had included some kind of top-down branch. Some models were including, for instance, face detector, car detector. So nowadays you have computer vision algorithms that are pretty good to do that. So they introduce that already in their model to improve their prediction. They introduce also some kind of, they call it top-down, but I'm not sure I'm supporting that. It's kind of bias, like the equator bias. That most of the people look the things in the equator, and that seems to be kind of robust. Some try to investigate how it is influenced by the content, and especially if you have faces, human faces, how this equator bias is moving a little bit. So they have kind of, yes, complex model to do that, and the best model for the prediction of saliency map of the head were including this type of information. But of course, if you go for more specific tasks, that's, I mean, you use the image for specific things, then you have to reconsider these things, yes, definitely.
Okay, thanks very much.
Thank you. Okay, thanks once again.
Thank you.
So we move to the second speaker, and the title of the talk is Objective Quality Metrics for New Immersive Media. This is the title which I was already trying to put forward, and the speaker is Dr. Federica Battisti from University degli Studi Roma 3, where she also received her PhD degree on the topic of multimedia data hiding based on human perception characteristics, and her main research interests are signal and image processing with a focus on the subjective quality analysis of visual content.
Thank you, Atanas. Thanks, Atanas, for the introduction. Can you hear me? Okay. Okay. So thank you. The video was easier than Patrick's one. So what I'm going to try to discuss today, even if it has actually been discussed quite a lot with Patrick earlier on, is the definition of objective quality metrics for new immersive media. So as Patrick was mentioning, there's a lot of ongoing work for subjective assessment. So still, we are pretty far from objective quality metrics. I'll give you some hints and maybe some ideas on how it will be possible in the near future to develop these kind of metrics. So first of all, we are talking about immersive media. So we are dealing with some content that is completely different from 2D. And it has also differences with 3D. So we need to take into account some peculiarities that haven't been considered so far. So first of all, what is immersion? Because everything starts from there. We are talking about something that is defined by Sadowski and Stan in 2002 as the feeling of immersion, whether physical or psychological in nature, allows the sense of belief that the user has left the real world and is now present in the virtual environment. This means that when I'm exploring some immersive content, what I have to feel is the presence feeling. I'm in that place, and I don't have contact with the world that is surrounding us. How can this be achieved? Well, there are many, many techniques, and like a basic one can be simply with a 2D screen, or more sophisticated and technological ones, like the one that you see on the top part of the slide. And eventually you can have interaction with the content itself. You can move around your site, see around the things, and this is, of course, an increased experience with respect to classical 2D and even 3D. This gives a feeling of interaction, but not really immersion. But this can be obtained by the use, for example, of head-mounted display. So HTC Vive is something that is largely used, or any kind of this head-mounted display. So you put them on, and you are projected in a completely virtual world. How can you explore this world? There are several ways of interaction. So you just stand still and rotate your head, as Patrick was describing earlier. So you have this kind of feeling that you can explore like a 360 content. Or you can eventually walk. So with the HTC Vive, you have these positioning capabilities, so you can walk like on a treadmill. And I know you have one here in the CIVIT lab. So you can walk in the virtual environment as if it is a real one. Well, this is a lot of stuff to process, and introduces a lot of, let's say, freedom and difficulties in assessing the quality of experience. In fact, as Patrick was showing earlier, there is a lot of work that is ongoing, and there's a problem in understanding how also the different techniques that we use to render this immersivity are affecting the quality of experience. So first of all, if we want to go to objective quality, we have somehow to start from the subjective one. So you will find some overlapping with the things that Patrick already said. I'll try to focus more on these objective quality metrics. So as with Atanas, the discussion with Atanas was highlighting, there are actually many, many ongoing efforts. These are just a few of them that I wanted to list. So there are standardization bodies, but also simply, people that are grouping and making their effort trying to define subjective and objective qualities. So for example, the first two are Callet is actually an ongoing working group. It was a cost action that ended in 2014, but they kept their activities going. And they have created this task force on immersive media experiences. Same thing, we have a VQX, so Video Quality Expert Groups, that has founded this immersive media group. And parts of the things I'm going to tell you today are actually an outcome of the talks we had with this group in the past weeks. Then we have, of course, JPEG Plano that is dealing with much larger aspects, so many things more than simply quality of experience. Then you have IEEE. Here I have listed two of them. One is the one that Patrick was mentioning. This is HFV, Human Factors of Visual Experience. And this is a group we're working on, so we're trying to figure out how to subjectively and also objectively evaluate the quality of immersive media. And of course, MPEG. And there is a joint effort between Callet and VQX trying to figure out how to mix these subjective studies with objective ones. And then there is this ITUT that I really haven't found. I found that it has been built up. It started activities in October, but not really information about the current activities, but it's a group on quality of experience on virtual reality. What is going on in these groups? Well, the first thing that has to be defined somehow are the guidelines that need to be followed to create objective metrics. And the first thing, this is something that we were discussing also in the previous talk, is that we cannot escape from being dependent on a specific task or an application. So what has been discussed in this VQX group I was mentioning earlier is that probably we might consider different groups to like big areas of application or task that can be used. The first one is, we call them unidirectional use case. It means that you have a user that is interacting interacting with this immersive media, but doesn't really have a feedback. Like for entertainment, I can wear my head-mounted display, I can watch around and explore the content, but I don't really have a feedback. Or for training purposes. Then we have a more difficult task, that is the bidirectional use cases. That means that there is an interaction between two parties, and there we start having a lot of more problems that have to be dealt with. So for the moment, for example, we started investigating the unidirectional use cases on the subjective side, trying to move to bidirectional and then eventually come up with a quality metrics for this. Is this fair, I mean, to go for specific task-oriented application? Atanas was asking, yes, but there are so many variations. How can you finally say this is good, this is not good? Who will say if this is well done or not? Well, this is something that's been already done, like for VQM, so video quality metric tools that has, for example, 5 models that could be applied in different use cases. So it is difficult, of course, it increased the levels of freedom that we have in the definition of quality metrics, but it's kind of mandatory for this type of media. We cannot escape from the dependence from the specific use case. So what are the steps that have to be followed if we want to create a quality metric? Here there are some rough guidelines. So first of all, and this Patrick was mentioning quite clearly, that we need, for a specific use case, that we select a database. And this is one of the biggest problems, because finding suitable databases, and not only simple database, but with ground truth and extra information that can help also to assess the quality of the metric that we have defined, is very, very tough. For 2D images now is okay, 3D is better, but for immersive media, I'll show you later on, it is still a big problem. Then we have to find ways to characterize this content, and I'll come up to this later on for light field in specific case. Then the definition of quality factors. So if we have some content, what are the characteristics, the quality factors that we want to explore? And I will give you an idea of this in the next slides. Once we have decided what are the quality factors that we want to assess, which is the purpose, what do we want to assess, like the coding techniques, for example, this has to be defined. Once we have clearly decided all of this, and this is also a pretty tricky task, we can actually start building up our subjective experiments, go through a bunch of tests, collect the mean opinion scores, and then check if our model that we have created can actually fit the subjective results. So basically, we cannot escape if we want objective quality metrics for the subjective part. This is where we are starting our work. So first of all, what are the quality factors? When we think about quality in general, if I ask you, what is quality for you? I think that the answer would be most likely audiovisual quality, because this is something we're used to. If you look at your mobile phone, you get like a video, and then you have to say, yes, it's good or not. You're going to go for audiovisual quality, and basically visual one. When it comes to immersive video, there are some other parameters that we should include, of course. The first is the presence, the sensation of being there. So when you have an immersive experience, I think most of you have tried this, you really want to be there to feel immersed. You don't want a contact with the outside environment. The real world has to be the virtual one. And this is something that's been actually investigated since the 90s. It's not something new. And there are, if you look on the internet in the state of the art, there's a bunch of questionnaires that you can use to assess the feeling of presence of users. Well, there are many questionnaires. We have done some experiments in our university, and I can assure you that it gets pretty tricky to select which one, because depending on how you want to assess the presence, the feeling of presence, and also the questionnaire changes quite a lot. Then the thickness, this is something that it's worth mentioning, but it was already there for 3D. So of course, if we find a way of assessing the thickness and to understand what are the factors that cause the thickness, then we can eventually embed it in a quality metric and help us to predict the subjective opinion. Then also the effectiveness should be included. This is a bit tricky also as a definition, because how effective is the system in providing this immersive media with respect of doing it in real life. For example, for training activities, this is pretty easy to understand. If I'm training, like we're planning to train firefighters for a specific task, how is it to train them in a virtual world rather than in a real world? The feeling has to be real to be effective. And of course, this is also depending on the hardware. And on this side, for quality metrics, it gets a bit difficult to take into account. Once you've done this, so once we have we have selected what are the quality factors that we want to address, then we have to go on what we want to evaluate, which is the purpose of our immersive media. And so, for example, should we take into account the capture system? For those of you who are in the 3D TV Con, we have seen that if we want to record like 360 content, you have several ways you can do that. And changing hardware also changes the quality of the content that you record. So this is one factor that should be considered, and also the post-processing, all the stitching, that generation, and so on, are slightly dependent on the capture system that you use. Same thing for the audio. Compression and transport. So this is pretty for you. I think it's pretty easy to guess how this can affect the quality. The display system that we're using, and not only the type of display, but also the rendering system, and I'm going to give you some highlights on this later on with some work we did also with Patrick. And then eventually bidirectional use case. In the bidirectional use case, we have this end-to-end delay. So we need it to be as fluent as possible, because we need it to be real smooth and natural. So where to start? There are so many parameters that should be selected, and first of all, the use case, it gets difficult. So what I want to show you today is like some work that has been done on virtual reality, but basically 360 images, and actually it's partially overlapping with what Patrick was showing you earlier, and then some work that we did for light field imaging. There is some, let's say, preliminary work on augmented reality, but they were still pretty far from going to subjective and even objective quality metrics. So starting from this subjective part, I'm trying to go to the objective one. So as Patrick was saying, if we want to define quality metrics, we have to start from good visual attention modeling. This was one of the goals of the Grand Challenge he mentioned earlier that was organized for ICME 2017. And I have to say we participated. It was a very interesting competition. So we started facing the problems that 360 offer. But I think that one of the most interesting outcomes, together of course with all these 30 or something visual attention models that are, by the way, online, they've been published, and actually there is this signal processing image communication special issue all dedicated to these saliency models. This is the important factor, the important study that came up from this challenge. So as Patrick already said, it helped us to understand how a viewer actually explores the content. The focus is not in the center. There is this offset of 14 to 16 degrees from the center. And this is extremely important for objective quality metrics, because as he said earlier, there are some metrics that are actually modified versions of PSNR. And this could be very nice to include this model, this attention model, inside the classical PSNR to see what happens and if the prediction of the subjective score is actually good or not. This is not the only outcome of this Grand Challenge, but together with that, there is a pretty large database, so containing head movement and eye tracking information, ground truth, and this is really important for the community. So I think the main two things to pick up from this Grand Challenge are this for this year. Let's wait for 2018 and see what will happen next month. So once we have these, how can we exploit it? The classical approach when new media come up, this is something that's been done also for 3D, is to start using conventional 2D metrics. So there is this, the Ibrahimi's group was doing this in 2017. This was a paper in which they investigated the performances of classical 2D quality metrics on this content. So we have PSNR, SSAM, and Patrick was explaining also the problem with this metric and some variations of it. Then we have PSNR, HVS, and HVSM that are modifications of the PSNR that are based on the human visual system, and both of them have been decided here in TUT, so I wanted to present them. And this is like a starting point. Together with that, some new metrics started appearing. So the answer to the question that Sebastian was posing earlier, yes, they are free. I mean, there are 3, 4 of them, and I have some references. Yeah, the code is downloadable, so can actually be implemented. And the first one is the spherical PSNR that is based basically from a conversion from equirectangular to spherical representation, and then back to equirectangular. And the error that is computed between this representation and the equirectangular one is considered as an evaluation of the quality. It's actually a PSNR, modified PSNR that is used. There are 2 different, let's say, versions of this metric, and they basically depend on how the mapping from the spherical to equirectangular shape is done. So whether it is using the nearest neighbor approximation or interpolation. Then we have 2 more. One is the one Patrick was presenting, so weighted spherical PSNR. That is basically a PSNR in which a weight is added, just to take into account this, let's say, equator bias of the viewers that we have demonstrated with the donut shape that is not really like that, but this metric has been developed in 2016. And then we have a cluster parabolic projection PSNR, CPP PSNR, that is basically PSNR, but only in this cluster representation. That is the one that you have for the world map. So you project the sphere on this, the equirectangular information on this shape, and then you compute the PSNR in this field. What are the results? Where the comparison between the performances of the 2D quality metrics and the doc-defined quality metrics, as you can see, is not so different. So if we use traditional PSNR, that we know that is not the best way to assess quality, and then we check it versus the ad hoc quality metrics, there's not this big difference. Same thing goes for Spearman correlation, and also comparable values of RMSE are there. But is there an explanation for this? Of course, yes, and it's pretty easy. This is due to the fact that, as I mentioned earlier, those metrics, the ad hoc design ones, are basically the modifications of PSNR. So you can see that the trend is the same. And if we want something that is performing better and can actually take into account different characteristics, then we should move from the PSNR and introduce something that is completely new. We are trying to get there, but still there's a lot of work first on the subjective part to be addressed. So this is the conclusions up to now. This is 2017. No recent work has been done on this so far, so probably there's a lot of space for trying investigating these aspects. So this is one part. The other thing is light field quality. I'm not going to talk about light field because I know that there will be Atanas who will talk about that later on. What I'm interested in when we're talking about light field are these capabilities that the use of light field provide. So there is change in viewpoint and refocusing. This gives a lot of opportunity for providing immersive exploration of a content. So this is why I put them in this, let's say, objective quality for immersive media. What is new here in the light field image communication chain with respect to traditional ones is the last block. So we have always our image, preprocessing, coding, distribution, decoding, and then we are here. We have these post-processing steps that depend basically on the way the content is displayed. So in the basic case, we get only the central views of all the available ones in the light field, and we get a simple light field as a 2D image. Or we can take different views and play them in a multi-view scenario, or we can exploit all those other information and, for example, have a 3D representation. Depending on this, we change the way the quality should be assessed. So where to start? We had this discussion with Patrick some time ago, a couple of years ago. So it is, how can we start thinking about evaluating light field? So the first problem we had is how to design properly the subjective tests that have to be carried out. And we said, okay, let's go first, deciding what are the visualization techniques that we want to use, then how to select the content that we will include in experimental result, in the experimental test, and then run the subjective experiment to see how our selection were working. And this is how we approach the problem. So first of all, how can we render light field content? There are several ways, but we wanted something that was easy. I mean, if you are home and you get light field content, which is the cheapest and fastest way of exploring and using the capabilities of light field, is displaying it on 2D displays. So this is the basic. You lose some capabilities, but still it is something that everyone, it's also easy to do on the subjective experimental premises that we have. So among all possible representation, we chose this one. So the extended depth of field, this means among all available view, we took only the central one. Then we had a pseudo video that now stopped playing, but basically we took close views, views close one to the other, and we played them as a video. And then we had refocus video. It means we looked, I'll try to play it again. So the refocus video is not playing, but what happens here, the camera is still, so we take one view and then we refocus at different depths. And so we have a different representation of the content, and then we picked, in this case, randomly refocused images from the available ones. Once we selected those visualization methods, we had another problem. So it is, how can we choose the sources that we want to use? Well, we had this work done in 2017, and we said, okay, light field content is completely different. I mean, it has the characteristics of 2D content, it has some characteristic of 3D content, and still has something more that doesn't belong to these previous categories. So we should consider all of them when selecting the content for our experiments. So we group them in these macro groups that are low-level features and high-level features. And among these, we had like 2D classical indicators that we use, plus, let's say, light field and 3D indicators. For what concerns low-level features, what are we talking about? Basically, like contrast, spatial information, all those features that you can easily extract with many metrics that are already available in the state-of-the-art. And then we went through the attributes that are specific for light field content, that is depth properties and refocusing feature that we have seen earlier. When it comes to high-level feature, for 2D, again, it's pretty easy. We talk about the type of content of the scene, indoor, outdoor, natural, computer graphic. While when we go to light field, we had to take into account things that we couldn't find in classical 2D, like the presence of transparencies and reflections, for example. And those are all things that have been included in our source selection. Based on this, what we did is checking up the state-of-the-art and the available data sets. And again, here we went into some troubles because at the time of this study, there were not so many light field databases available for our studies. And we took 8 light field images. And from this, we said, okay, we will compute all the features all the indicators that I've shown in the previous slide. And this is the results of low-level features for 2D. This is just one example to show that we computed spatial information and colorfulness, and the images that we selected as source content are spread on all this plane. This means that we did a good job because the sources that we were using were kind of were varying quite a lot, and so it was a good choice. Based on this, then we said, okay, let's create, starting from these selected light field sequences, some distortions that can be applied. What are the type of distortions that we can address? Of course, compression and the addition of Gaussian noise. For compression, we use JPEG 2000 HVC Intra. The goal was to apply those distortions in order to have target PSNR values. So we created our data set starting from our sources. We did these modifications, and we used the visualization techniques that were shown earlier. We use an ACR method, assessment method. It means the subjects were just standing still and seeing one image at a time with different visualizations, and they were rating the quality of the thing they were seeing on a scale from 1 to 5, so from poor to excellent. And overall, we had 20 subjects as a preliminary study. What did we find out? That actually the users preferred the extended depth of field. So you have a light field, and what you like the most is the 2D image that is extracted from the central view. And this is basically due to the fact that users we are used to see 2D content, so this was the most familiar way we could see it. But then the second most preferred one, this is actually what we were interested in, is the pseudo video. So the collection of all views, focused ones, and played in this video shape. So we said, okay, nice thing, but there might be a problem. So we selected only a specific collection of views. But as Patrick was saying earlier, if we change the trajectory, then maybe also the quality changes, so we will be in troubles. What can we do? Consider different ways of putting all the views together. So those are the light fields, and we investigated these 6. Of course, this is not exhaustive. This is not dependent on the specific application. So it's like a general indication of how we should show the content to the users for subjective test. What we did this time is not using our content selection method, and this was actually a mistake, and I'll show you why. And we took 11 light field images, this time from a data set that is available from EPFL. So Turaji Ibrahim's group was sharing this data set with ground truth, so it was a pretty large one. So we decided to pick this one, and it is a large one organized in groups. And we picked one image from each group in order to vary the content and some other 2D low-level features. And we use the 6 visualization techniques I've shown here. So pseudo videos, collecting the adjacent, the views, the frames with in different ways. This time we had 28 subjects, same quality of subjective assessment method, and we used 3 different frames per second. So we wanted to check whether by changing the number of FPS, this could have an impact on the perceived quality. Well, the results say that that we didn't like that much, but we could still find some conclusions out of it. So first of all, if we go through the visualization techniques, there was a slight preference, we can say, to this PV option, that is this one. While they didn't like at all, they disliked the most, let's say, this NO representation. Okay, this is a spiral. This can be easily explained because when you move in this direction, you actually change a lot. So you have consecutive frames that are changing quite a lot in position and sometimes in illumination. And this doesn't give a very fluent appearance to the video. So this was not perceived as a good one. Probably with some post-processing, this could have been better. So we said, okay, pseudo video, the closer are the views, the better the quality that is perceived by the user is. But then we were looking at the mean opinion scores. So as I said, the scores are from 1 to 5, bad to excellent. And as you can see, all of them didn't go over number 3, so over fair. All of them are pretty low. So we started wondering why. And luckily, we had asked also the subjects to give us some comments. And apparently, the problem was on the content that we were showing. So we were investigating, again, this spatial information versus colorfulness, for example. And we found out that all the images that we've been using were kind of belonging to the same cluster. So they were not nicely spread as for the previous work. And this might actually be an impact, may have an impact on the result of the subjective test. So content is still something that has to be very carefully selected when running subjective tests. So what we found out here, that there's a lot of work to be done, further analysis on the content, and we will eventually rerun this subjective test. And there's another aspect that should be considered, the difference between interactive and passive experience. So when you show a video, a pseudo video, even if it is obtained by different views for this light field, it's still a passive interaction. Okay, it's, yes, a passive interaction. I mean, the user can't really choose where to look and when to look at that. So interactivity will be much more interesting. On the other side, assessing the interactivity gets really, really hard because everyone will have his own experience, and it will be difficult then to have a common background and to compare the results that you get if you leave the user to freely navigate the space. So there are many challenges here, and we will try to deal with this in the near future. But first of all, we have to clearly find out all the details concerning the subjective part. So it was like Patrick was presenting the subjective quality assessment. I was this objective one, but as you have seen, there are many overlapping things. And this is due to the fact that objective cannot exist without subjective. And then once subjective is well consolidated, then we can think about abstracting some quality metric that can work without having to run every time subjective test that we know is time consuming and you need a lot of people, and it gets very tough to get those guys coming and sitting and assessing our experiments. So first of all, we need an understanding of the subjective perception, and then there are several parameters that should be considered. Among these, the application scenario, so the specific target use case, the quality factors that we want to investigate, and which is the purpose of our study, and which is the effect on QoE depending on these purposes. And this is an invitation for everyone who's working in this field, and provide your data sets as much as you can. The best thing will be containing ground truth, mean opinion scores, but we can eventually collect the mean scores by ourselves, and eye tracking info. There are efforts there already, like in the ACM Multimedia System Conference that will happen next week in Amsterdam. There are a few years that there is this open dataset and software track. It's very nice because you have people publishing their contents, and they're freely available and can be downloadable. So it's a pretty nice thing. And both Qualinet and BQEG, of course, JPEG Plan as well, have collected a number of data sets. I've underlined this one because those efforts have been going on for quite many years now. So if you go to these websites, you get very, very, very large list of data sets of any kind. With this, I think I'm done. Thanks for your attention.
Your questions, please.
Yeah, I have the problem that all the questions you already answered.
All your data sets were captured with Plenoptic cameras, right?
Oh, our data set, you mean are in Roma University? We have one that has been captured with Litro Illum, yes. And yes, it was actually a joint work with Sundsvall University. So it's them, we did this database, but it is like a small one, and we found out that there are things that should be improved. All the ones that I have presented here actually are not part of the data set we personally recorded, but they were taken from available ones.
But still everything is from Plenoptic
Yes.
cameras.
Also, the EPFL data set is taken with Illum cameras, and it's very detailed. You have all the information there to use it properly.
Okay, other questions? So it seems that pick a scenario is not that bad for omnidirectional content.
Well, the thing is, yeah, I knew that this question was coming because then the correlation values are not so bad, but then it was 0. But this is not true. I mean, I think it depends also on the content that they've used, because as Patrick was saying, if you move things a bit, then the performances can change quite a lot. So I had other reference papers that were doing this kind of comparison, and PSNR was definitely lower. This one I liked because I had the metrics, the ad hoc design metrics, and.
But then it means that the methodology is questionable. So
That's the point, yeah, also. So this is something that should be investigated. There are so many.
No, but as you stated, it depends also on how you evaluate the performance of the metric.
Yeah.
And the statistical framework that has been used here,
Yeah.
let's say, is in favor of some.
Yeah, this is why it was tricky to see the PSNR is so well performing when we have been saying that it's not working. But
okay. More questions? If not, thanks
Thank
once
you.
again.
okay.
Our third talk is about immersive quality assessment in virtual reality streaming. And the speaker is Dr. Igor Curcio from Nokia Technologies. He received a PhD degree in signal processing from Tampere University of Technology, and in 1998 joined Nokia, where he is now Bell Labs Distinguished Member of Technical Staff. He has been lecturer in video compression at TUT, and has been active for more than 15 years in 3G, PP, DLNA, IETF, MPEG, and some other acronyms showing expert groups, where he also covered sub-working group and task force chair positions, co-authored over 200 standardization contributions. He has about 300 granted international patents and scientific publications, member of ICM, IEEE.
This one?
Has been in the organizing committee and TPC of several international conferences. His current interests include immersive media services and standardization of omnidirectional video communication protocols in MPEG. And while reading your bio, you just prepared to start the talk, so you have the floor, please.
Thank you, Atanas. Good morning, everyone. I realized that when I did this presentation, I forgot to add the first slide, which is a slide with the table of contents. So I have here my table of contents slide, and this is the list of topics that I'm going to talk today. There are 6 topics that I will touch today. I'll talk about viewport-dependent streaming, about challenges for test methodology for subjective assessment of 360 video. And then some experimental results on viewport-dependent streaming for bitrate reduction. And then I'll present some visual fatigue results. And then I will introduce a metric which we have experimented in our labs. It's called the Similarity ring metric. And then a few words about asymmetric video for VR and some results. So there are quite many slides that I have. I hope that I will have enough time to handle all topics. But the main idea is to give an industrial perspective on this topic around streaming and with some results. Does it work? Okay. Okay, now it is on. Yes, so it should work. Let's see if this works. And this one works. Okay, so I'll throw some problems that we have in this area as the challenges of 360 video compared to traditional 2D video. First of all, we have more challenges in terms of bandwidth. So videos are getting larger and larger compared to normal 2D videos. That's a problem we have always had, but now it's really big. Then the second thing we have as a characteristic of 360 video is that when we are consuming videos over with a head-mounted display, we only watch a viewport. So we only watch a subset of the whole 360 video. And that's one thing which we always have to take into account when consuming this video, but also when assessing the video in both subjective manner and also objective manner. But then there is also another problem. So how to ensure that the results that we get, for example, subjective results, can be comparable to each other. If I'm watching during a test assessment, if I'm watching most of the time in this direction and another person is watching in this direction, how can we compare these two sets of results? It becomes a challenge. Now, the system we have been using in this our experiments is a typical streaming system where you have on the left side, you have a server side where you load the content, you have a content description, and then on the right side, you have the consuming part. You have the client part, which is typically a user with a head-mounted display. We have used the configurations with Gear VR, so with the phone mounted on the head-mounted display. And then, of course, depending on the orientations of the head, the content is then viewed according to that orientation. So there are some elements that are giving interactivity. Now, the concept of viewport adaptive streaming or viewport dependent streaming, there are different terminologies, but basically the meaning is all the same. What does it mean? It means that in order to save bits, streaming bits, people had the idea that whatever you are watching and is in front of you, within your viewport, within your head-mounted display, is streamed at high quality, and whatever you do not see, which is in the background or in the remaining part of the 360 area, is streamed at lower quality. With this little trick, it is possible to save already a lot of bandwidth. But there are challenges, because whenever you turn your head and you change your direction, you are looking for the highest possible quality. It takes some time to get that highest quality. This is different from the approach of viewport independent streaming, where you have all the time the same constant quality for all 360 degrees, but of course it costs more bandwidth. So there are two important parameters here that are playing an important role in this game. One is the viewport sizes. How large viewport are you watching? If it's too large and you are streaming too much data, then of course you need a lot of bandwidth. If it's too little, then for every motion you do to the left, to the right, up or bottom, you have a viewport switch, and then you may experience lower quality. It's a trade-off, and it requires, of course, a careful setting. And the second thing is motion to high quality delay or motion to photon delay. There are different terminologies also here. I like to call it motion to high quality delay, which is the delay that it takes between the time you move your head and the time you have in the new position the high quality content, which may be high resolution content or high quality in terms of QP level. And that's also a challenge for the system because the system reaction time should be as low as possible. Now, in terms of challenges for subjective quality assessment, people that are doing subjective tests, sessions, they need to have enough time to assess the video. So this is one thing that has to be taken into account. We are not anymore in front of a TV. We are not anymore in front of a computer screen, but we have the whole 360 around us. So we need to have enough time to look at this content, to assess this content, but not too much, because we forget. And if we forget errors, for example, there is the forgiveness problem, which is, of course, something that we have to avoid when giving scores and doing assessment. And also, we have the problem of having manageable test sessions, which cannot be too long. And then, as a last point, we need to have a way to have a fair assessment within the same subject or between different test subjects. Like I mentioned before, if a subject is looking and testing in this direction and another subject in a different direction, we do not have comparable test results. So we want to make it as comparable as possible within the same subject or between different subjects. So the basis from where we started in our experiments was to look at the ITU specifications, so the standards specs for subjective assessment. And none of them is good. None of them is perfect for omnidirectional video, so they needed to be adjusted or extended in some way in order to support omnidirectionality. The test environment is different, so a typical environment is such that the person can move, maybe sitting on a chair, but can move over the whole 360 space. And the pre-screening of the test subject, we have seen this is a quite important thing because some people are actually unable to perform those tests. They get sick very quickly or they get motion sickness, so we really want to avoid those side effects. So we have been using in our experiments the absolute category rating with hidden reference as a method, which has also been used in literature by other researchers around. And the collected results, which are visual quality scores, visual comfort, and post-test visual test questionnaires. The results which I have here do not include visual comfort scores. Now, from the methodology still from the methodology point of view, the thing which is important to tell to the people that are doing assessment of 360 video is that they should score only the important thing and try to forget about software crashes, flashes which may happen during watching sessions, or stitching artifacts, because unfortunately the stitching is not perfect in some cases, but they should not score, of course, the stitching artifacts, because these are not part of the scoring goal which we have. Test sessions duration about 25 to 35 minutes. We saw that this is the limit people can really handle head-mounted display, perhaps divided into different parts, maybe 10 minutes, 15 minutes, but for a total of about 35 minutes, that is, let's say, the maximum of sessions wearing head-mounted displays. And then visual fatigue questionnaires are quite important before the test and after the test in order to understand what are the effects of these tests. So the pre-screening. Pre-screening, of course, we need to avoid situations that create motion sickness. So we try to exclude subjects that are more sensitive. And then we have performed also some preliminary tests to those people to check, normal vision tests, color tests, contrast tests, and stereoscopic vision in order to make sure that the results are correct. One more thing that which we have been recording is the interpupillary distance. This, in order to have even more data to analyze in case this data is needed. And this is how it looks, a typical test session. We have the instruction part, then pre-test visual fatigue questionnaire. We do a training, some training with some sequences which will not be recorded in terms, they will not be, they are scored, but they are not taken into account in the statistics. And then we have blocks of sessions with stabilizing sequences in the middle in order to have statistical stabilization of the results. And at the end, there is a post-test visual fatigue questionnaire in order to understand the difference between the beginning and the end of the test. One more thing we have been doing is recording the head-mounted display orientation. So there are two ways. Either you get raw yaw, pitch, and roll data, or if you have access to the whole viewport information, then you may record what viewport is watching the test subject at any point of time. One more element that we have been putting in order to have comparable test results, we have been putting a little constraint about the motion direction. Because if everyone is free to watch whatever they want at any point of time, it becomes very difficult to compare those tests. So we have been instructing our subjects and tell, please follow this motion from this position, central start position, then going to the right about 180 degrees at your own speed, and then come back to the other direction at your own speed, and then end towards the center, which is the start point. It's a little constraint that made our life easier. These results have been published last year in the workshop within the ACM Multimedia Conference. And basically, the idea was to reduce as much as possible the streaming bit rate of viewport-dependent streaming, but we wanted to understand the different cases. So there are two questions that we wanted to understand. First of all, how do you perceive the quality difference when you're moving from this position to this position, and in this position there is a low quality for a little amount of time? How do you perceive this difference in the case that the background, so the background quality is lower quality in terms of QP level, so SNR quality difference. So foreground tile, high quality, background tile, what you don't see, but what you may see for a little while is at lower SNR quality. In the first question. The second question, we wanted to understand whether it is better to have in the background SNR quality degradation or a degradation in terms of spatial quality. So we ran an experiment. These are the parameters we have been using with Gear VR and Galaxy Phone S8 with 3 different video sequences in the sport domain, adventure domain, entertainment domain. The sequences were about 20 seconds long, 30 frames per second, HEVC with independently encoded tiles, 4K resolution, stereoscopic, 12 people with us. And we have been fixing the maximum bit rate to 23 megabits per second. This is the tiling scheme which we have been using for a panorama view. So we have a top tile, we have a bottom tile, and then we have a background tile. So the frontal part was 120 degrees, which was the part that was streamed at high quality. All the remaining was at lower quality. So whenever you were moving up and looking up, you needed to have a little time to load the high quality. And that was the experiment we were interested in. So that was a little time and how that quality was perceived. So the, the different quality levels were 4, and they are summarized in this table. The foreground view was always at high quality, and the background was either at lower quality in terms of SNR quality or at lower quality in terms of spatial resolution. This is results that we have when we think about what's the pattern people have been watching. So this is the head motion pattern between 12 people. And it tells basically the yaw in the yaw dimension. You may guess, we may guess, but just a guess, that people have been watching approximately the same thing at the same time, because you see that there is some sort of correlation in the curves. So you see that with those instructions we gave, start from here, move a bit to the right, about 180 degrees at your own speed, go back to the center, and go to the left again, and then end in the center. With those instructions, people have been watching approximately the same thing at the same time. Now, these are the DMOS values results, which tell that basically for decreasing QP quality, the subjective quality decreases. Nothing exceptional. This is as expected. Perhaps maybe less expected is the fact that in this case, when we have low resolution, if we increase the quality, the QP level with low resolution, we don't get better scores. So basically the conclusion which we found is that if you want to save bits for viewport-dependent streaming, and you want to have foreground quality, high quality, and background with some sort of lower quality, you better use SNR quality reduction rather than resolution, low resolution in the background. We had two examples that we can compare. We have a DMOS value of 4.5 with the full resolution versus DMOS of 4.2, so approximately comparable. But we see the difference is at 10% between the low resolution in the background, 34%, and the low quality, the low SNR quality in the background. So we concluded that we could have about 44% streaming bit rate reduction with the DMOS level of 4.5 with SNR quality reduction. And this is the first set of results. Then, what about visual fatigue results? So we have results about the questionnaires that we have been asking the people. And these are the results, well, these are similar parameters which we have been using. And this is, again, the same motion pattern that I've been following. So this is the table of the results. And you can see that we have been asking different questions. The question was, with respect to the beginning of the experiment, do you experience stiffness, head pain, dizziness, concentration problems, nausea, sleepiness, eye pain, eye fatigue, focusing problems? Do you have dry, wet hair? Do your eyes look into different directions? Do you have problems with clear vision or double vision? So, luckily, nobody have been reporting problems in terms of the last three. And few subjects, they responded that they have problems with the questions 1, 7, and 9. And then some other 25 to 33%, they had problems with other But maybe the most severe symptom was dizziness, where more than half people was experiencing some amount of dizziness. Okay, so the next topic is, I want to reconnect to the beginning when I said how to make sure that people can watch the same thing at the same time. This is actually a relevant problem with 360 video, because people can always look around, and then we need to have a way to make sure that people, the test results of the people are comparable. So we need to have a way to determine within subject correlation and also between subject correlation. Basically, do people watch the same thing at the same time if they are testing the same clip or different clips? This is what we wanted to know. And I again want to propose one of those curves, which is a head motion pattern for the same subject, but in different test conditions. So how do we understand this data? To understand whether a subject has been evaluating well 12 times the same sequence or not. This is telling a little bit that the subject has been following some sort of pattern, but we will need to have a metric. So the metric which we found and we called similarity ring metric is explained in this slide. Essentially, if we have all curves, this is an example with 12 different subjects, and if we want to make sure that they look the same thing at the same time, we want to ensure that those vertical bars contain the curves. So these are the rings. So imagine that this is a ring, and those are the ropes that you want to pass through that ring. So if those ropes pass through that ring, then it means that the people have been watching the same thing at the same time. This is, of course, not true in all cases. We can see that we have calculated that in this case, it's only 68%. But anyway, it's a quite good number already when we say that about 70% of the time, people have been watching the same thing at the same time. So this is the essence of this metric, which is measuring the similarity of how much people have been watching the same thing at the same time compared to himself or to other people. This is telling another set of results with a similarity ring metric for all genres that we have been testing for 3 clips, and it's basically a total average of 67% with some peaks that are around 80%, which is pretty high actually. So we have been achieving quite high results in terms of similarity. Of course, the higher is the number, the more confident you are that the results you have been getting are correct and then they are comparable. So here, if we can find some conclusions, methodologies we have today for assessment of 360 video are not complete and exhaustive, so we need to have more elements. One of these elements may be the similarity ring metric, which we have been testing in our labs. If you want to have more details about this metric, you may look at that document. And the last thing I have for today is a quick snapshot about results, which will be presented next week in the ACM Multimedia Conference in Amsterdam. We have been testing asymmetric video for 360-degree video. Of course, asymmetric video has been tested as in normal 2D video, 3D video, and so there is already some results for many years. But we wanted to somehow repeat those experiments and see how what are the values that we can count on when we have head-mounted display with us mounted, and then doing some sort of asymmetry between left and right, or how we can play with the foreground and background. Foreground and some sort of asymmetry between foreground and background. So basically we found that if we consider DMOS, average DMOS value, those values which I had circled in light blue, we could have a DMOS value of 4.4, then we could achieve a bitrate saving of about 30% for an asymmetry level which is 23, 27 in terms of QP. So those are QP for left and right. You may think that you don't want to have asymmetric video all the time if you don't want to compromise quality and don't want to degrade from a value of 5, which is excellent, down to a value of 4.4, right? But then you may use this technique for adaptation purposes. So in periods when you do not have enough bandwidth, you may want to sacrifice for a little while quality in order to have adaptation period and then go a bit down using asymmetric video. We have been looking also at eye dominance. Is it relevant whether you are eye dominant, right eye dominant, left eye dominant in these results? No, it doesn't matter in these results that we had. So we have been experimenting this, and basically it does not make any difference. And the last slide I have, and then I conclude it, is about streaming background only tiles with asymmetric video quality. So the previous results I showed you were about asymmetry, where I have asymmetry between foreground and background. Here I have asymmetry between only in the background. And I can see from these results that for a DMOS value of 4.2, I could achieve another 15% bitrate saving. So if I put all together, all the different asymmetries all together, maybe I could achieve even more. So if I have about 30% in this case, and then 5 to 15%, I'm getting close to 40% in terms of compound results. So these results will be in the ACM Multimedia Conference in the Packet Video Workshop next week. I don't know if any of you is going there. For sure is going Alice there. Patrick as well. Okay, so I'll see you there. That's all I have. Thank you. Maybe I can save some time for the next presentation.
Thank you very much. Okay, your questions, please.
Yes, I have a bunch of questions. If I may,
We have plenty of time.
Okay.
Please go ahead.
So about these asymmetric techniques, so that's pretty in line actually the fact that eye dominance is not influencing factor. That's something that we also observe for stereoscopic content.
So you have same result?
Yeah. It has been published in transactional broadcasting, actually TOB, but that was not for 360, but that's so it's good to see that
there is alignment.
That's good, yes, because it was always this discussion and some people are using some kind of trick.
Yes.
They switch left-right asymmetric conditions.
Yes.
So I guess that here you always put the quality on one eye and
yes, it's easier. Yes, it is easier.
Yes.
Basically, this table says that there is a difference of 0.08 DMOS value, which is basically insignificant. So there's no difference.
But I have one question, because here you are measuring the mean opinion score. Did you use also the questionnaire that you use in your first experiment about sickness, fatigue, and so on? Because one possibility of such technique is that it triggers some kind of cognitive effort, because it's true that we are playing with binocular rivalry.
You mean for the asymmetry?
But it's not doesn't come as a free lunch, right?
Yes.
It means that the brain has to deal with that, and if you use this trick too long, then it may have some effects.
Exactly. Yes, in this experiment we have not done the questionnaire.
I understood that you want to use it in short amount of time.
Yes, you may use it for adaptation purposes. Then it's basically not
you are not
giving
doing-
any,
okay.
any
So
impact, yes.
So you don't have the data for this, but
No, I think we
Okay.
don't have. Harry, do we have this data? I think not. For the stereoscopic, I think we don't have in this experiment, we have not done that
Okay.
questionnaire, yes.
that would be interesting because there are some people are suspicious that this is, you cannot play too long with this type of trick. And
Yeah,
it would be
I
nice to
suspect the same.
identify what is the time window before you trigger some.
It could be an interesting
civil,
experiment.
And I have another question. Can you give more details about this ring similarity metric? So
Yes.
I think it's very yes, in line with some of the. Well, first of all, that's how we can control the trajectory of observers and to achieve some kind of.
Yes, so the idea would be to
influence.
put that constraint that we
Yeah.
have been putting about the direction,
Okay.
which could be anything, but some form of constraint,
Okay.
such that the people would be more or less aligned on
Yeah.
the same viewing pattern.
Okay.
And then this, using this metric for calculating the similarity. I can point you, I can give you a document where there is more
Okay.
description about
Okay.
how this is
So
calculated.
it's a comparison of trajectory of each observer.
It's calculated point by point.
Point by
so
point.
it's instantaneously. It's a calculation of point by point from the
Okay.
the time
Okay.
point of view. So if, for example, we have been sampling the head-mounted display movements every 100 milliseconds, so
Okay.
we take every sample point at every
Okay.
sampled
Okay.
data point for 10 people, 12 people, and then we analyze what's the
Okay.
distance or the
Okay.
correlation
So I'm
between.
curious to look at the details because
Yes.
that's a big trend also these days also to find some way to compare this trajectory, and you can also decompose eventually this head trajectory as a set of let's say fixation and saccade, but head saccade and head fixation. So there are few methods to compare this type
Yes.
of things when you do this. So
Yes.
yeah, I'm curious to.
Okay, I can point you this, and then I think we can even talk later during today.
Thank you.
Okay, thanks
Thank
for
you
the
very much.
comments.
More questions?
Just a question about the streaming. The first experiment, you're saying that you asked not considering buffering problems or something like that. How
Yes.
did you succeed in doing this?
The best that we could, of
So
course.
you didn't,
We had to rely on the subjects, so we were informing them, but of course we had to rely
but
on the
did you
subjects.
experience any delay or buffering problem during the experiment?
You mean from the implementation point of view? It might be that sometimes there are some flashes because there were no software crashes. This is I'm sure of that. So the software was pretty stable, but occasionally there may be some flashes, which I think they are given by the phone. So some strange events, which could be a flash. So we wanted to make sure that this event is not scored either in a positive or in a negative direction. So we were informing the people, please do not take this into account. Do not look at the stitches, at the stitching errors, because you don't have to score that. There were no crashes, and there were actually no extra delays or rebufferings in our environment because we were using a wireless LAN access point, some sort of isolated environment. So there was no cross traffic. So basically, it was a dedicated network for that.
Okay, thanks.
Could I just ask about this questionnaire? Your post-fatigue questionnaire, thanks very much, is asking a person to make a rating or an assessment of a symptom in relation to that they felt at the beginning of the test. Is that correct?
Yes.
Did you consider asking the person to make a rating at the beginning and at the end, and then subtracting the difference in the ratings? So the same questionnaire at the beginning and at the end, and then looking at the change in the rating over the questionnaire.
The rating was not numerical. It was yes, no.
Oh.
So the difference, it was not easy to calculate the difference. So the questionnaire was, do you feel nausea? Do you have dizziness? Yes, no.
So not a scale of do I feel nauseous, not at all, a little. You're not rating the amount of...
Oh, okay. So, yes. this is the questionnaire, yes. So if you think that this could be a numerical, yes, this is. But we have not made the difference.
There were so little symptoms, just 1, 2, 3, so it was insignificant.
I'm just wondering how you could expect somebody to remember their level of these symptoms 20 minutes previously, when they were looking at, or at the beginning of the thing. You're asking them to remember the level of these symptoms, these 10 symptoms, and then make a judgment about the feeling of those now compared with what they were at the beginning?
Well, at least there was the scale was telling a little more, the same, a little bit less, so there was some sort of relation to how it was before when we say the same. So, of course, we were relying on the subjects. But I think the point of having a way to make the difference could be interesting. Maybe we have to think about if you convert this into numbers and then we find the differences, it could be some interesting study.
They had so little symptoms in before, so it won't change the results. Just very, very little.
It may be quite difficult actually. If you ask a person how nauseous you are right now, on a scale of 1 to 5, what is your base case? You don't know what the base case is. What is not nausea and what is nausea or mediocre nausea. So those problems might come when you ask such a question.
Okay, I think it's good input. Thanks.
Other questions? Okay.
Okay, thank you very much, Atanas. Thanks a lot.
We now proceed to the last talk, and
that's a good point.
It will be given by me.
Thank you. Thanks.
So we'll need this 1 minute to switch the presentations and to take the microphone, and then we'll proceed. No, I don't.
Oops, the microphone.
You could copy the last version.
Atanas.
Yeah, thank you. This is the DSLF.
Yeah.
Yeah.
It was this one.
Perfect. Thank you. Okay, this talk is going to deviate a bit from the previous ones, as it is more focused on things we can do with light fields and in recreating visual cues. So it is not that much about studying the subjective experience and quality of experience in immersive media. However, it somehow contributes to the topic. So I will briefly introduce the light field as we formalize it, then light field displays and how they recreate 3D visual cues. I will focus more on the epipolar plane image representation and format of densely sampled light fields, which we like to put forward, and how we can reconstruct it from a sparse set of cameras. So we usually start with this Plenoptic function, which is the 7D function representing all rays traveling in space, parameterized by their location, direction, wavelength, and time. And we usually drop the wavelength and time because we can work with trichromatic representation of color, and then we can play with sequences. And if we consider this propagation in half space, we end up with parameterizing the rays through their coordinates when they are passing through two parallel planes, which are usually associated with camera plane and image plane in an image-based representation. So such a parameterization gives us a way to think of rays either in their Cartesian coordinates or in their polar coordinates, where for small angles we can directly replace the angle with its tangent. So depending on the application, either Cartesian or polar coordinates might be preferred. And we can also consider how rays propagate in space. When put them as samples in this ray space coordinate system, such propagation is usually related with the shearing operation, which will play a role later when we speak about the epipolar plane representation. So what we usually do when we deal with light field displays is to study first how human eyes sample the light field, and we can represent the position of the eyes over the array space, and then consider how they move, and this will give us a kind of ray space sampling related with the human visual system. And then from the other side, we can try to model the light field displays as recreating the same light field on the same coordinate system, or matching what the human visual system can see. And essentially why we are interested that much in light field is because light field can be the tool for recreate more visual cues. What we know from earlier attempt that stereoscopic 3D or binocular 3D recreates only the stereopsis, the binocular visual cue. It usually fails to recreate the focus cue and the continuous parallax. So focus cue is related actually with two phenomena. One is the accommodation. One, the crystalline lens are forced by muscles to change the shape in such a way that the point in certain depth gets in focus on the eye. However, there is also the other effect called retinal blur, when points which are at different depths appear like blurred on the retinal image. So usually these two effects work in accord in the human visual system, and this is how we perceived elements, objects in focus. And then if we start moving the eyes, like the retinal image will change, and then we'll have the effect of motion parallax. Actually, may I return here? So what we require from light field displays is to ensure this ray directionality, which will support the focus cues and the motion parallax. So we need tools, we need technologies which will exactly ensure both spatial and angular sampling and reconstruction. And there are different display technologies aiming at doing this. We can look at integral imaging, and actually the common part is that you need to have generators. In terms, it can be some 2D display. It can be TFT or LCD or some other matrix, and then you need to have modules which ensures the directionality. So it can be, for example, a sheet of lenslets, and these are the cases of integral imaging or super multi-view displays. Or you can have also differently positioned projectors at certain distance from the screen, recreating this directionality. Basically, differences are how you ensure this directionality. For example, in the super multi-view display, the focal plane of the microlens is positioned as the viewing plane, and then the pixel behind the microlens contribute to different view images. So one has to take care of how pixels corresponding or rays corresponding to different directions are combined together. And usually what we need in such display is that we need a high number of views. So in contrast to what actually Federica was presented, we are looking at light field as something which can support more visual cues. So we are not interested in showing flat 2D images, but interested more in how we can develop computational tools for faithful reconstruction of these rays from the real world imagery, and then to support these displays which are still emerging. So these displays are still under development, but hopefully they will come in one or another form. So in a pursuit of way how to form or reconstruct a light field from real scenes, we come to this epipolar plane image representation, which is another way to look at parametrization and the rays in terms of two parallel planes. So the example is that we are having camera moving like from position A to B, C, D, and so on. So this will be different perspectives of the scenery. And if we order these images along the t-axis, we'll get a kind of three-dimensional structure. If we start moving the cameras also vertically, we'll get the four-dimensional structure. And then we can look at different combination of coordinate axes. Like when we look at the multi-perspective images, we see 2D images. However, if we combine the camera axis and one of the image axes in a slice like this, we are going to see this directional structure where different points at different depths transform into lines with a certain direction. And the direction is related with the depth where the points are. So you can see we can determine actually the direction by knowing the two camera positions and the corresponding projections at the images. So in a sense, epipolar plane image encodes the geometry of the scene into the shapes of these directional stripes formed by epipolar lines. Everything is very good until we, okay, this is something explaining in more details. Like if we make the slice here, like you can think of going into t direction, we are going to see a homogeneous image, so it is somewhere in the background. Then if we make the slice here, we are going to get the same points, their evolution along the direction of the camera motion. And when we make these different slices, we can see different structures of the scene encoded in different epipolar planes. We can do the same in vertical parallax as well. So in this way, we are going to have a 4D epipolar image cube, and we can get the combination of either of slices. What I wanted to say is that everything looks okay as soon as we consider this in continuous time. So this means infinite number of dense cameras, like any position of the camera. And if we take such an epipolar image and transform it into Fourier domain, the directions will transform into a specific support of the Fourier transform, which we can call bow tie or a fan, which is limited by the minimum and maximum depth of the scene and the focal length of the camera system. This is strictly for Lambertian scene with no occlusions. So then if we start getting occlusions, we'll see that this Fourier transform and its support changes. Now, when we start discretizing the Fourier transform, which means placing discrete number of cameras, and each camera has a discrete number of pixels, we are periodizing the spectrum. So in spatial domain, it will look like this, and in the angular domain, it will like this. So we get all possible replicas, and our light field reconstruction task is to be able to preserve the baseline and to get rid of these replicas. This is good when we have dense cameras and dense pixels in each image, because then the replicas will be further away from each other. However, we may experience also the case when the cameras are sparse, and then the replicas will overlap, and we'll end up with aliased representation of the light field. So the discretization in spatial and angular domain impose these challenges. So if we want to recreate smaller features, we need more pixels. If we want to recreate closer objects, we need denser set of cameras. And then optimal sampling and related with reconstructions depends on our application and what we want to reconstruct. There is this figure, which is quite well known from the seminal paper on Plenoptic Sampling. Then we either work with more images or with more depth layers. And there is always compromise how we sample. Do we sample a higher set of images, or we go at sampling higher or dense number of depth layers? When we encounter occlusions, the support of the Fourier transform of the light field gets wider, and we need better tools for its reconstruction. And here is actually the time when I want to comment on the what we called densely sampled light field. When we start moving the cameras to position the cameras at different perspectives, this is like the sampling interval, sampling distance between cameras. This multi-perspective representation appears in form of pixels being projected at different pixel positions. What we'll see as a disparity between images. So if we put the cameras further away, like the disparity, like this is like disparity of 3 pixels. So the point project on pixels where the disparity vector is 3 pixels. If we go close enough, like less than 1 pixel or 1 pixel at most, then there is no ambiguity in putting the line, in putting the epipolar line. Here, we don't know exactly where to go here or here. And with disparity less than 1 pixel, the lines are formed unambiguously. So this is actually what we want to achieve. We want to be able to form the epipolar lines in an ambiguous way. Otherwise, we'll have to deal with some other tools if we want to recreate the continuous plenoptic function. Here we can deal with simple linear interpolation if we need to create arrays different than the array on the densely sampled grid. So our task is to recreate all images which are in between the given ones. So if we start with a set of captured views, which is sparse, let's say coarsely sampled light field looking in epipolar image domain, we want to get densely sampled out of this one. In terms of Fourier transform, this means that the replicas will be nicely separated, while here the Fourier replicas are overlapped. So we are dealing with this aliasing. If we get the views and put them together, like dealing, for example, with views which are 16 pixels disparity away, if we put them together, we will see this kind of staircase pattern. If we put them at the proper places with respect to the densely sampled light field, we can see that the lines start to form. But we can see because we are human, so we know how to get the entire from patches. But how to tell the algorithm or the computer to continue the lines. So it seems that this is a problem which can be cast as an in-painting problem, like in imaging. When we have holes, we want to in-paint the holes. And one modern tool for solving in-painting problems is to go through sparse image representation. So what we want to achieve is the following. So we want to find, let's say, Y is our image. We want to find it in some representation in terms of some dictionary. So these are, alpha is representation of the image with respect to this dictionary. And we want to find it in such a way that when subsampled, the difference between the representation and the given image is minimized. And we minimize it along with looking for such a representation which is sparse. And this will ensure that as soon as we can find a representation which reconstruct the given samples, we are good. Also given that the sparsity is ensured. So our dictionary is formed by what we call shearlets. Those are compactly supported time frequency atoms. So in space domain, they look like oscillating filters. And in Fourier domain, they look like differently oriented multi-scale filters. So we have one atom responsible for the low frequency region, and then we get different scales, and in each scale we'll have several directions. So we can go further, we can increase the Fourier, the support, and we can support more directions and at higher scales. So having such a dictionary, we can say, we can slightly change the notations because they follow in the next slide. So we say this is our shearlet transform. So we have a direct transform which takes the image and decompose it into a set of coefficients. And then we have an inverse transform which takes the coefficients and reconstruct the image. So these transforms, they exist in terms of sampling theory. They form a frame, so the reconstruction is ensured, and so on. So we can this is an equivalent formulation of our problem. So find the sparsest representation in shearlet domain, which ensures that our image can give the same given views. So H here is this masking operator which takes sparse sampling from this densely sampling. Such problem is solved, like the sparsification is done usually through thresholding. So what we are going to do is to take our image into shearlet domain and keep only the significant coefficients and zero the other ones. And this is usually done through iteration. So at each iteration, we subsample the image. We take the difference with the given views. There is one factor responsible for the convergence. Then we add it to the given iteration. We take it into shearlet domain, where we threshold it, and then we reconstruct it back, and this is our next iteration. This turns to be quite powerful in filling the holes. So if we start with something which is very low frequency, so you see after each iteration, we are getting more and more details. So like the blue or the turquoise rows are the given views, and all others are views to be filled by the procedure. And in terms of views, this means that we can start with 16 views, and then I'll try to run it once more, but it seems that no, it doesn't start. So the idea is that we show the input views, and we show the reconstructed against the ground truth, which seems to be quite the same. Recently, we managed to reconstruct even non-Lambertian scenes, which is usually impossible with interpolation dealing with depths, because in the case of non-Lambertian scenes, the depth might not be unambiguously defined. So for example, reflective surfaces, the shearlet atoms are quite capable of reconstructing the intensity. So you can see here it rotates. And here is a zoomed-in version, where you can see that these areas are quite nicely reconstructed compared with one of the state-of-the-art methods. This is a difference image showing that much more details are reconstructed than in the state-of-the-art approach. So just to conclude, we are looking at light field technologies as candidates for recreating 3D visual cues. So we believe that immersive visual experience is possible if all visual cues are recreated in a synchronous way. So we need to have stereopsis, we need to have focus, we need to have continuous parallax. And the tool of doing this is to be able to generate dense enough set of views, correct views. And we specifically have developed such a computational imaging tool for reconstructing densely sampled light field. And given a particular display, then we can pick up the rays which are needed for the display. The procedure is still slow. in parallel implementation, it takes seconds, so it is still to be further developed to run in at least in interactive times or real times. And then, of course, there are other challenges related with what exactly light field display technology can be developed. Whether we need lenslets, whether we need projectors, or some holographic elements, or something which will support the desired directionality of rays. Okay, this was the last slide. Thank you for your attention. Yes, please, questions.
Do you have any idea how many number of samples you require to basically reconstruct using the shear lifts, the continuous representation?
Theoretically, we can start with quite subsampled set of images. So experiments like the images are separated by, let's say, disparity of 64 samples. Yeah. It will require more layers of the shear-led decomposition because you have more candidate directions. And then you need to introduce more layers. So let's say when your input images are close to each other, then you need to have atoms which are dealing with the corresponding directions in things like this. If you start having these holes wider, then you have to test all these directions, which means more scales and more directions, which increases the size of the dictionary, the number of your atoms. Also, you need to have more views. Like in the procedure, in the thresholding procedure, we keep the given samples, like here. Like they work like pillars. So you always enforce the existing things in order to steer the directions which each of next iterations. So as you see in the demonstrations, the details are being restored, like from stronger to weaker to more details.
The second question I had was, you told me that you also did some experiments on non-light measurements. This one. You said reflections, basically.
Yes.
Have you tested anything on transparencies?
Semi-transparent, yes. So we have already, I didn't show this example. Semi-transparency is like you have an object and in front of it you have another object which is semi-transparent. Again, if you try to find the depth in such a scenery, this is very challenging. You cannot have an ambiguous depth associated. Yeah. Yes, yeah. We have such a demonstration in the lab. Sometime we can show it also on the big light field display. This type of decompositions are dealing quite nicely with it because they are kind of combination, signal expansion in terms of coefficients. So it is like the intensity which is seen in the multi-perspective images, and they are able to handle such cases. What was more surprising for us, because initially we were thinking that such problems with reflections won't be easy to handle, because in the reflection you actually change the directionality in a kind of orthogonal direction. So you need atoms which would support this direction. However, what was actually discovered that we can scale the scene and shear it in such a way to confine it within the support of the dictionary we have. So it is a matter of a technical tweak to put the scenery in such a way that in terms of a shearing operation, it will be inside the reconstruction atoms. And then they are able to handle it. Then you have to de-shear it to reconstruct it in the proper views and proper images. Of course, the challenge is to find out how much you need to do this, to shear it properly, which depends on different factors. And
so,
yeah.
I'm just imagining if you have a scene where you have non-Lambert-Eban objects that are moving around. So
this is still static. We haven't experimented with non-Lambertian moving objects. This is kind of very interesting and has to be tried. Yes, please.
So, yes, the Callet dictionary looks very, it's pretty smart because it's kind of systematic dictionary and seems pretty nice fitted with this EPI representation. But you partially answer one of my questions, that was how you deal with this reflection stuff. But do you think there is a room for learning new dictionaries, so not less systematic learning a dictionary?
Yes, they are. Currently, there are plenty of works taking this path.
Yeah.
So you can train your dictionary, and you can train it on light field patches. So there are such works where the patches can be either 4D patches, which are kind of following also the when they are considered in epipolar image domain, they are patches which will reveal the directionality. And then you need to have a good training set to build the dictionary. So then the task will be to find simultaneously the dictionary and the coefficients. So you have to learn the dictionary. This is the task of sparse coding. Yes.
If you, so I introduced one of our methods that was using convolutional sparse coding.
This is, we have followed several works which are focused on sparse coding and learn dictionaries. One of our aim is to compare with them. They perform extremely well if you have a very good training set. If you have a feature which is not in a training set, you won't catch it in the normal. So what you mentioned, this systematic way is exactly the alternative path. So we are dealing similarly what was done in imaging with curvelets, contour nets, all other directional LEDs, which aim at ensuring certain rate of approximation when you are taking n coefficients of the representation. Here, the good work which was done is to recognize that such directional elements and multi-scale elements are very good to tile the frequency space. But of course, we also have like there are different problems in this. So we have to work. For example, we call it sparse, but it is not. In practice, you need to use all coefficients. So you get like 30, 60 coefficients per sample when you are doing the reconstruction. All right. If there are no other questions, this was the last talk of this quick workshop we organized. Thank you very much for your attendance, And we hope to have more of this in the future because the area is quite interesting. Thank you very much.
I'm inspiration.